হ্যালো।
হ্যালো।
হ্যাঁ, শোনা যাচ্ছে কথা?
জি ভাই, শোনা যাচ্ছে আপনাকে।
ওকে।
তো
খুবই সরি,
আমি
আমার ল্যাপটপটা আমি এখনই চেক করে দেখলাম একটা রিসেন্টলি আপডেট এসেছে, এই জন্য আমার ইয়ের ভিডিওটা কাজ করছে না। ল্যাপটপের ভিডিওটা আমি ফোন দিয়ে কানেক্ট করছি।
আচ্ছা।
অলরাইট, আমি কি স্টার্ট করব?
জি ভাই, তার আগে আমি জাস্ট একটু ইন্ট্রোডিউস করে দিই।
Sure.
সো আমি ইংলিশেই করি। So welcome everyone to MMMRN webinar. So after a long hiatus, we again started this webinar after term final. So today we have with us MSR Sadi Bhai. So he is a proud graduate of MME department of BUET. So Sadi Bhai is currently graduate fellow and pursuing PhD at Rice University in the Department of Material Science and Nanoengineering. So he completed his MS in Mechanical and Aerospace Engineering at George Washington University. So in his undergraduate and masters, he focused on polymers and have developed some interesting studies. And currently, he is working in Professor Ajan's group at Rice University. And he's working on the development of high performance and sustainable biocomposites using additive manufacturing technologies. He has published several incredible journals in different high impact factor publications. And recently he published in Advanced Materials a review paper on direct inwriting. So we are very proud and we are very privileged to have him with us. Thank you very much for giving your time. So we can get to your presentation, right?
All right. Thank you so much, Ridul, for the wonderful introduction. You guys all can hear me and see the screen, right? Can you hear me?
Yes, maybe we can.
Okay, all right.
Yes, we can hear you.
All right. So I'll just go ahead. Ridul already gave a pretty good introduction. I'm Sadi, and today I'll be talking about valorization of asphaltenes. Again, Ridul already gave an introduction. I also prepared some bio for me. I'll just still quickly go over. This ugly looking guy is me, Sadi, and I did my master's in MME from BUET, my undergrad, and then my master's in mechanical and aerospace engineering from George Washington University, and currently a PhD student in Rice University. So I will just quickly get into the technical details. Asphaltene, first of all, I'm going to spend a good amount of time in building the background story so that all of you who are currently involved in research in different sectors can get a hold of the talk. So yeah, let's begin. Basically, we need energy every day for our day-to-day activities, and for any type of advancement, be it technological or cultural, we need energy. And this pie chart here shows the contribution of different energy sources that is contributing towards fulfilling the global energy demand. And as you can see that the petroleum oils is consuming most of the areas of this pie chart, the 34% share. And the way we get these petroleum oils is basically there are these deposits that have been forming for millions of years underground due to various geological and biological reasons. And so we are extracting those underground crude oils and the petroleum industry is basically refining them into cleaner fuels, which we're putting into our cars and using for regular activities. And during these refining processes, the byproducts that comes out, from the petroleum industries are called bitumen or sometimes asphalt. And within this bitumen, a significant portion is this molecule called asphaltene. We're going to learn more about asphaltene. The interesting fact about asphaltene is that it does not have a specific structure or chemical nature. So the one that you are looking at here is just one of the many hypothesized molecular structure of asphaltene that people use. But in general, it is a heavy macromolecule that has this aromatic ring-like structure. It has this aliphatic chains, then the heteroatoms and various metallic impurities. Like I said, it does not have a specific composition. Here is an example. In this study, the researchers showed that asphaltenes from different geographic locations have very different compositions and atomic ratios. And also in a study by atomic force microscopy and scanning tunneling microscopy, the researchers showed that asphaltenes itself can have very widely varying molecular structure. So basically what I'm trying to say is that this is a complex molecule which does not have a specific structure and chemical nature. But what type of problem does it create in petroleum industries? Like I said, because of its heavy nature, during the petroleum processing, it precipitates out, and as a result, they get deposited on the pipelines, thus jamming the pipelines. Also, the petroleum processing involves a lot of catalytic reactions. So these asphaltenes have been reported to disrupt those catalytic reactions. Cokes are unwanted in petroleum processing. Asphaltenes have been shown to act as coke precursors, and due to its heavy nature, it also increases the viscosity of the heavy well. As a result, impacting the economy and the efficiency of oil processing. Let me show you two pictures of how asphaltenes can cause serious problems during oil processing. You can see that it's jamming pipelines and these bores in a significant way. So these are the type of problems that asphaltene create in petroleum industries. And because of these detrimental effects, petroleum industries often treat these byproduct asphaltene as a waste product. And typically the way they are processing asphaltene is either they recombust to use as fuel for their internal transportation system, or they discard these asphaltenes into tailing ponds and landfills. And as you can guess, both of these processes emit significant amount of greenhouse gases and impact the climate. So at this point, different types of environmental and governmental agencies are putting pressure to these petroleum industries, telling them that you need to take care of your waste, otherwise we're going to shut you down. So this is why the petroleum industries are now, desperately trying to reuse or find some values for asphaltenes. And that's why, that's when we come into the picture. Rice is known for its for carbon material research. So at this point, we approach these petroleum industries and we tell them that if you give us asphaltene, we can try to find some values or uses of these asphaltenes. We can try to make carbon fibers, and also we can try to make graphene from these asphaltenes. So, and today I'm going to talk about both of these routes. First one being the carbon fiber production. Any researcher or scientist would ask, like, why someone would try to make carbon fibers from asphaltene. Carbon fiber is already an established technology. It's already commercialized, and it has already found application in automotive and space applications. And here are some of the precursors that are typically used for carbon fiber production. which are rayon, and then there is polyacrylonitrile PAN and Mesophase peach-based precursors. Among these precursors, PAN grasped the majority of the market, almost 80%. But if you look into the Mesophase peach, and asphaltene as a precursor falls under this Mesophase peach category, has a very high yield of 75 to 85%, almost double than what we have for PAN-based precursors. So because of this high yield, we are interested in converting these asphaltenes into carbon fiber. And here, this is a flow diagram that gives a very basic picture of the steps involved in producing carbon fibers from this petroleum asphalt. And in the region, this red squared region shows the very essential 4 steps that are involved in carbon fiber production. Basically, if you read any book or any review paper on carbon fiber production, you will see that there are 4 essential steps, which I will talk about in the next slide. But even before this essential 4 steps, there are some additional steps, like before these 4 steps. These steps are usually the pre-treatment strategies. And these are pretty important because this is the step where we try to adjust the molecular weights and chemical compositions. We try to get rid of the unwanted particles, and we try to form Mesophase pitch, which all of these things like significantly impact the carbon fiber production, each step of the carbon fiber production. So the pre-treatment strategy is very important, and one of our goals in this project was to determine and optimize the pre-treatment strategy for asphaltenes. And regarding the Mesophase pitch, which is also a newly introduced term, I will explain in detail soon. So for the pre-treatment strategies, I have noted down some of the important factors here that needs to be taken care of when you develop and optimize the pre-treatment strategies. Basically, your precursor needs to have very high carbon content, aromatic content, impurities, low impurities and low molecular weight distribution. And these things are very much intertangled. That means if you change one of these factors, the others are going to change, and that in turn is going to affect the whole carbon fiber production route, the 4 essential steps. So speaking of these 4 essential steps, this is the first step, which is called the fiberization. Basically, this is the step where we have the precursor material, and then we extrude it at some high temperature in a fibrous form. So this step is called the fiberization. It typically happens between somewhere between 150 to 250 degrees Celsius, depends on the materials, definitely. The next step is the stabilization. This is the most critical step in carbon fiber production. Basically, after the first step, after fiberization, the fiber that we get is a thermoplastic fiber. But during the second step of stabilization, here we are oxidizing these thermoplastic fibers. We are cross-linking them and converting those thermoplastic fibers to thermosets. And this is necessary because the subsequent steps, for example, carbonization, which takes place around close to 1000 degrees Celsius, you have to give the fibers some kind of stability to sustain at that high temperature. So the stabilization is the step where we provide the fibers those stability so that it can sustain the carbonization. And the last step is the graphitization step, which happens around 2000 degrees Celsius or even more. During the carbonization step, carbon content significantly increases to around 85 to 90%. And during graphitization, the carbon content increases even higher and goes to around 99%. I introduced the term Mesophase, and I wanted to discuss about Mesophase also a little bit. What is Mesophase? Basically, the precursor that we have, or any peach-based precursors, are initially isotropic in nature. They do not have any kind of molecular orientation within themselves. But by Mesophase formation, I mean that we have these aromatic planar molecules, and if we can stack the planar molecules on top of each other through pi interactions, we are going to have something like a graphitic structure, but this is an organic molecule, and we are going to form this crystalline micro domains. These domains are called Mesophase. This is very important in carbon fiber production because these Mesophase domains are the ones that will help attain this graphitic structure at the end of the fiber formation. And these graphitic structures are very important because the mechanical properties of the fibers depend on this type of ordered structure. The next question would be how these mechanical properties would depend on the orientation of the particles. That would be my next question, or anyone's next question. So I'm going to explain a little bit about that also. For example, if you have a graphite-like structure and you take one graphene sheet out of it, the mechanical properties or the elastic properties are basically isotropic in nature. That means if you measure the properties from any angles, you're going to have similar mechanical properties in that plane. But when you have a graphitic structure and you measure the mechanical properties along certain axes, the mechanical properties, for example, here the Young's modulus becomes a function of the theta. Here, theta being the angle between these basal axis A and the stress axis, or the axis along which you do the tensile measurement. And this is often presented in the form of this equation where you see the relation between the modulus and the theta, and the S is the compliance here. And people have already calculated the mechanical properties, basically the compliance and the stiffness in this case for graphite single crystal materials along different directions, and have got different properties. Now, by saying that, in this picture will give you a even better idea that, for example, for a single crystal graphite, when you have all the graphene sheets aligned, for example, suppose this is the fiber and you are doing the tensile test along this direction. So in this case, your theta becomes 0 because all the graphene sheets are kind of parallel or 0 degree with each with respect to the stress axis. And if you are able to align all these particles along these axes, then you see you're going to get a very good very high mechanical properties. On the other hand, if there are some kind of misorientation, then the angle is going to increase and your mechanical properties is going to go down. So this is, I wanted to show this because this shows why the orientation of beginning from the organic molecules till the graphitic sheets in carbon fiber is very important, because that's what determines the mechanical properties. So this was all the background that I wanted to discuss for the carbon fiber production route. Next, I will dig into the kind of research that we have done for carbon fiber production. So the samples that we received, asphaltenes came in two forms. One was the powder form, which looked like this, and the other one was the gel form, which looked like a gooey-like substance, kind of like this. And if you remember, I discussed that at some point that the pretreatment strategies are very important for any type of carbon fiber production. So our first goal was to develop the pretreatment strategies. And so we tried different type of pretreatment routes for both of the samples. For raw powders, we tried heat treatments, which would generate like polymerization, air blowing, basically heat treatment in presence of air flow. And for gel samples, we tried solvent extraction and vacuum treatment. And all of these strategies were meant to achieve higher thermal stability, because the one very critical criteria needed for carbon fiber production. And from different tests, finally we chose two samples. One was the raw powder as it is, and then the other one was the solvent extracted gel for making carbon fiber. The tests that helped us determine these two samples was the NMR, XPS, FTC, IR, MS, which is so NMR is nuclear magnetic resonance spectroscopy, XPS is X-ray photo emission spectroscopy, and this is Fourier transform cyclotron ion resonance mass spectrometry. So these tests helped us determine the key factors that I explained at the beginning. For example, NMR gave us the aromaticity index, how much is the aromatic compounds present in the solvent extracted gel and raw powders, how much is the aliphatic contents. XPS gave us the elemental composition, and FTCI-RMS gave us the molecular weight distribution, more information about aromaticity. And so from this, we determined that yes, the solvent extracted gel and raw powders can be used as our main precursors. After we determined this, we had to investigate the rheological properties. Basically, we tested the viscosity of both of the samples at different temperatures and at different shear rates, and we optimized. We found the sweet spot, basically, which would be necessary or we would be utilizing for carbon fiber spinning. We looked into the thermal stability. As you can see, the solvent extracted gel was used because the gel sample had a very low thermal stability compared to the solvent extracted gel. So in summary, I'm not going too deep into the numbers because this would take a lot of time, and I do want to cover a good amount of. I want to share the results. So, but the core idea is that we took this asphaltene, did several types of physical-chemical characterizations, and we determined the spinning parameters, which helped us extrude these green fibers in this form. We were able to extrude fibers with diameters ranging from 10 microns to 100 microns. And even towards the end, we were able to spin fibers in the form of these spools in large and bulk quantities. After the green fibers were formed, the next step, if you remember, was the stabilization. Here we tried different types of stabilization routes, single step and multi-step stabilization. One thing is necessary to remember that during stabilization, oxygen, we are doing oxidation, and oxygen kind of diffuses from the surface towards the inner core of the fibers. And so the more oxygen you diffuse, it kind of goes from the outside radially towards the core. So you need to make sure that you have the proper fiber diameter and other parameters during this stabilization step, so that the whole fiber is oxidized, basically. And so we tried different types of stabilization routes, and the one that worked was the multi-step stabilization. And we used FTIR, Fourier transform infrared spectroscopy, to confirm that that the fibers have been oxidized by, for example, here before stabilization, after stabilization, we saw this ether stretch. Again, here we saw an additional peak that corresponds to the carboxylic acid peak happens when you oxidize these fibers. And then also these OH groups, they diminish because now the oxygen, after stabilization, the oxygen are involved in bond formation with carbon. So the OH group peak is kind of diminished. We also did XPS. We saw that after stabilization, the carbon percentage decreased and oxygen percentage increased, which again gave us the proof that our fibers have been oxidized properly. This is another proof that we were doing SEM and EDAX, which is energy dispersive X-ray spectroscopic, which basically gives elemental composition. So this is the fiber cross section. And as you can see, that the carbon is kind of uniform throughout the surface, but oxygen is mostly present on the surface, but on the core, oxygen is not there, which suggests that only the surface regions have been oxidized, whereas the inner core have not been oxidized properly. And I'll show you the consequences. So this is the consequence. These are some of the consequences that after carbonization, which were done around 600 to 800 degrees Celsius, oftentimes we have found these hollow fibers. And this is a direct consequence of what we saw here. It happened because we were able to stabilize only the shell regions. The core regions were not cross-linked and therefore were not stabilized. And as a result, during high temperature treatment, the core regions basically evaporated, and we ended up with hollow fibers. We were also getting porous fibers, as you can see here. But anyways, we were towards the end, we were able to optimize all the parameters, and we were able to get this type of solid carbonized fibers with good mechanical properties. We reached Young's modulus up to 70 gigapascal, and the tensile strength was around 400 MPa, which is not the best, but if you consider that we are making these carbon fibers from a waste material, and this is one of our kind of first attempts in making carbon fibers from this waste material, I think this is a pretty decent number. The commercial carbon fibers typically have a strength from 1 to 10 gigapascal. I know this is not as great as those commercial fibers, but again, we are just now, we have just like recently started the investigation. Currently, we are mostly focusing on improving the mechanical properties. So that's all I have for the carbon fiber production route. Now I'm going to talk about the other route, which is asphaltene to graphene, and I am very, very interested to talk about this part because this part, I mean, I was the lead of this part, so I'm very interested to talk about this one. Basically, one professor at Rice University, Dr. James Tour from the chemistry department, recently he came up with this technique called Flatule Heating, which can convert highly carbon content polymeric substances into ordered graphitic structures. Basically, you put the precursors in between two metal electrodes, which is enclosed in a glass cylinder, and you apply a very high voltage, around 200 to 300 degrees Celsius. It depends on the material, but within less than 1 second, within a couple of milliseconds, basically your precursor is converted into these graphene-like structures. I do have a video of the process. This is a desiccator tube. Let me show you. This is a slow motion video. I'll just fast forward it. So yeah, this is how the process works, and basically we give this asphaltene powder as the input, and at the end of the process we get this kind of material, which for other substances the Tours group has found graphenic signals from the output material. So for our case, whatever we got from asphaltene, we had to check whether we have really formed graphene or not. And so for that, we did Raman Spectroscopy. Raman is a very good, widely used tool for confirming this type of graphene formation. And Raman showed that for AFG, which is the asphaltene flash graphene, showed the development of this 2D peak around 2700 weight number. So this gave us the idea that graphene has been formed, but we had to double check using other characterization techniques as well. We did TGA, thermogravimetric analysis. Asphaltene usually degrades at around 550 degrees Celsius, but graphene in general should have a lot more thermal stability. So when we did the TGA on the asphaltene-derived flash graphene, we got a very well improved result. We also looked into the XPS for elemental composition. As you can see from asphaltene, the carbon content from 93% went up to 98%, and the heteroatom percentages decreased significantly. We did XRD for getting the information about the crystallographic planes and their orientations. We saw the peak at around 26.1 degrees Celsius, which is typically found in graphene. We also looked on the transmission electron microscopy, TEM. TEM images imaging showed some of the flakes, and from the images we got the average lateral sizes of this graphene flakes, which was found to be around 25 to 30 nanometers. We also, from TM, we also saw the interlayer spacing between the graphene sheets, which was found to be 0.359 nanometers, which is a little more than what is obtained in AB stacked or Bernal stacked graphene or graphite. So this gave us the idea that maybe the graphitic structure that we have is not very pure form of graphite, and this is something in literature. Then we did some literature search and we found that this actually, what we are forming is not well ordered graphitic structure. Rather, we have randomly oriented graphenes on top of each other, and these are called turbostratic graphite. Going back to XRD, in literature, we found that when these two dotted lines, when the peak at these dotted lines kind of reduces, that's another signature of turbostratic structure formation. So from these experiments, we kind of deduce that what we have formed after the Flatule heating process are turbostratic structure, and this is important, why I will show soon. Now, I know in MMMRN, many of you do a molecular dynamics simulation. We also did collaboration with University of Washington, and they did some molecular simulations. So basically, they took one of the asphaltene structure, and here CB is carbon black, which was also added in experiments, because the Flatule heating is actually a resistive heating process. And for this process to work, we need the precursor material to be electrically conductive. Because asphaltene is insulative in nature, we had to add some carbon black, which gives the conductive nature. And so basically, that's why carbon black was added in experiments and also in simulation. So in the simulation, I have a video of the simulation. Basically, the asphaltenes and the carbon blacks were mixed together, relaxed, and then the temperature was ramped up to 3000 degrees Celsius, because that's the temperature that one reaches during the Flatule heating process. And as you will see at the end of the process, we are ending up with some of these ordered graphite-like structures. So yeah, here you will see those graphene-like structure. From these molecular simulations, we got a very interesting information about the Flatule heating process. That is, carbon black not only provides the conductive, the required conductivity, but it also acts as the nucleating agent. That means these ordered 6, 5, 7-membered rings, they start growing around the carbon black. So that was an interesting information that we got from the molecular simulations. We also got what other types of gases were being involved, were being evolved, and the 5, 6, and 7 membered rings being formed during the processes. So, like I said, the turbostratic nature was very important, because our idea was to show the funding agencies that we can convert the asphaltenes into graphene, and then we can use the graphene into different applications. So for showing the applications, we developed this polymer and AFG, asphaltene flash graphene nanocomposites. And because of the turbostratic nature, we speculate that we could easily get very well exfoliated and dispersed graphene sheets inside the polymer matrix. For forming good polymer composites, it's very much necessary to exfoliate these nano reinforcements and then disperse them well. So I guess the turbostratic nature helped us achieve that exfoliated nanocomposites. And after the composites were formed, we tested their mechanical properties. And as you can see, at 1 weight%, the mechanical properties improved compared to the neat epoxy. However, at higher percentages, the properties degraded. This is possibly due to the aggregation of these particles, because if you keep on increasing more nano reinforcements, at some point they start aggregating again, and which start acting as stress concentration zones and crack initiation sites. We also looked into the surface morphology using an ACM, where we saw a very smooth surface for epoxy, which is representative of a brittle fracture. But for the composites, we saw kind of rough surface, which suggests that there is a good amount of crack deflection going on, and you have better mechanical properties. Especially for 1-weight%, the surface roughness, if you consider the Z roughness, it's the maximum for 1-weight% compared to higher loading percentages, for example, 5-weight%. And that's why we suppose that the mechanical properties of 1-weight% is the best among these tested. Our group works a lot with additive manufacturing. I have also worked with, and I have been working with additive manufacturing as well. So we thought that if we can 3D print these polymer-AFG nanocomposites, one of the techniques that we use is known as directing fighting. It's an extrusion-based technique. In order to print any material using this technique, the material needs to show some kind of very specific rheological properties. However, for the pristine epoxy AFG nanocomposite, we could not see those desired rheological responses. As a result, we had to add a rheologic modifier, which in this case was a fumed silica. So after we added the minimal amount of fumed silica, we could obtain the proper rheological response. Basically, the viscosity needs to show a shear thinning behavior, and also then there needs to be a relation between storage modulus and the loss modulus. Basically, at low strain rates, you need to have the storage modulus needs to be higher than the loss modulus, and at higher strain rates, the opposite needs to happen, so that at higher strain rates, basically during extrusion, the material can flow, and after extrusion, it can retain the shape. So we obtained this type of rheological response after we added the rheology modifier, and we optimized all of the contents, and we were able to 3D print the architected structures, which look like this. Next, we investigated the thermal properties. Basically, we took the composites and we shine a laser light, and we record the temperature using an IR camera. And as you can see, with increasing amount of graphene content, the maximum surface temperature is reducing. This means that the material is being able to dissipate more heat as we increase the graphene reinforcement percentage. We did the time-dependent study also. Basically, we kept the light on and then off, on and off, and we kept on recording the maximum surface temperature, and we saw similar effect in the temporal test as well. But this test gave us the idea about the thermal dissipation behavior. We wanted to see if we can calculate the thermal conductivity from this test as well. So for that, we did COMSOL FEA simulation, basically simulation of laser heating with the laser having a Gaussian shape. And from this test, we can also obtain the single line profile. So we gave different types of material input. For example, here for epoxy, we gave the material input as the density of the material, then specific heat capacity, the other thermal coefficients, and we kept on tuning the thermal conductivity till the line profile obtained from simulation matched the experiments. And when we had this type of fitting, the conductivity that was used for this fitting was taken as the thermal conductivity of epoxy. And this thermal conductivity is also well within the range that is reported for that particular type of epoxy. And using the same method, we reran the simulation for nanocomposites also, the 1-weight%, 3-weight%, and 5-weight%, and we saw an increasing trend for the thermal conductivity. So this means that with increasing AFG, the thermal dissipation behavior improves, as well as the thermal conductivity improves. And this happens because when you have a low graphene content, basically they are not connected with each other, but with increasing graphene content, you have an interconnected network of graphene within the polymer composite, and that gives a better phonon conduction path from one side to the other side, and you end up with good thermally conductive composites. This is again another ACM image of the surface of the 5-weight% composites. You know, in 5-weight% composites, we often saw this type of graphene-like sheets stacked with each other, more like an interconnected network, which we did not see in 1-weight% or low-weight% composites. So maybe we speculate that these are those interconnected networks that we were talking about here. After the thermal properties, we also tested some functional properties, and these were done by our collaborators. I'm not going to talk much about it, but basically we applied this composite as a coating on steel substrates, and we also saw good corrosion resistance properties. Polymers are often used as a corrosion resistant coating to protect metals and alloys, but here we show that if we reinforce those polymers with a little bit of AFG or asphaltene-derived flash graphene, the performance can be even improved. We also did some quantification. Again, I'm not going to talk much about it, this particular thing. Lastly, we did some Lcnt analysis. Also, it was done by one of our collaborators, life cycle assessment, and TA stands for techno-economic analysis. The LCA shows that basically different types of environmental metrics that can be calculated. For example, how much carbon dioxide gas is evolving. Then there are other parameters. For example, freshwater eutrophication, acidification. We saw that these Flatule heating process performs significantly better compared to asphaltene recombustion. If you, again, talking about asphaltene recombustion, if you remember at the beginning of the talk, I said that the petroleum industries are currently treating asphaltene in 2 ways. One was the recombustion, and the other one was discarding in tailing ponds and lands. Quantifying these environmental metrics for discarding into tailing ponds and landfills would be difficult. So that's why we took the recombustion of asphaltene as the reference, which is shown here in the yellow colored bars. But for all of the metrics, we see that the Flatule heating is better in terms of environmental impacts. The TA also helped us determine the production cost of asphaltene-derived flash graphene compared to other Flatule heating precursors, and we saw a cost, like feasible cost for asphaltenes, and it's significantly better when you compare it with CVD grown graphene. You know, these are not comparable because the structures, the properties are very different. But if you look at the production cost compared to the different types of CVD grown graphene, it's significantly cheaper. So with that, I would like to end and summarize my talk. Basically, in our effort to convert a waste resource, we have taken asphaltene and converted it into carbon fiber and flash graphene. For the carbon fiber, we developed several pretreatment strategies. We determined the parameters needed for green fiber spinning, the multi-step stabilization routes that I showed was our own original idea. We came up with these multi-step stabilization processes that worked really well, that helped us do carbonization and get nice fibers with good mechanical properties. For the flash, after successful convert to graphene-like structures, we developed these polymer nanocomposites, which had good mechanical properties, thermal properties. Hello.
Hello. Yeah, we can hear you now.
Okay, all right. Can you see my screen?
Yep.
All right. So for the flash graphene, we developed the composites which had excellent structural and functional properties. we showed 3D printability of these nanocomposites. We also examined the environmental and economic impact, which turned out to be very good compared to CVD grown graphene and other Flatule heating precursors. Lastly, I want to thank Dr. Pulikala Jain and Dr. Raman for their constant guidance and funding support. And as you can see, I presented a huge volume of work, and this work was done in less than 2 years of time, which is pretty difficult to achieve without the help of many collaborators. So I have to acknowledge them. These are all the collaborators who helped us achieve whatever we have achieved from this project. So that will be all. Thank you all for listening. Please feel free to ask any questions.
Thank you very much, Sadibhai, for your excellent presentation. The work is really very comprehensive. It's a very big work.
Thank
so
you.
anyone would like to ask any questions, you can raise your hand, or you can also type your question on the chat. So I have one question, like in your presentation, I saw that multi-step stabilization worked pretty well.
Right.
So what were the problems with like single-step stabilization?
So basically, let me. No, I don't have to go there. So the thing is, you know, in asphaltenes, there are multiple. There is a wide molecular weight distribution. So if you are doing a single-step stabilization, basically you are not able to oxidize all the components. Whereas when we did a multi-step stabilization, it was like a step-by-step process. You know, at a lower temperature, you were able to oxidize a certain portion of your, for example, the lower molecular weight components. Then you increase the temperature, you soak it at that temperature. Then another type of another molecular weight percentage or fraction gets oxidized. You increase the temperature, soak it there. In this way, we were able to, I think, oxidize a multiple fractions of the whole spectrum of the molecular weight distribution. I think that's what worked.
Yeah. Right. And also, like in your when you used epoxy to make a composite like structure, we saw that the maximum strength came from 1% inclusion.
Right.
So after 1%, it gradually decreased. So what could be the reason for that? Do you think? What would be the reason?
Yes. Yeah, I think you know, once you keep on increasing these nano reinforcements like graphenes or other 2D materials, even CNTs, what happens? It becomes difficult to exfoliate and disperse these nanoparticles inside the polymer matrix. In order to get very good mechanical properties, you need very good exfoliation and dispersion as well. So I think when we increase the percentages, these particles, we could not exfoliate the aggregates. And as a result, if you have aggregates in your composites, that's going to act as crack initiation sites.
Right. Okay. Anyone have any question? You can raise your hand here, or you can also type it in here. I would say don't be shy about asking questions. Yeah. So we have Professor Dr. Mohammad Nasim Hasan, sir. Sir, please, sir, ask your question.
Do you hear me?
Yes, sir, we can.
Yes, sir.
Can I see the speaker of today's webinar?
Yes.
I actually, my laptop is not working, so I have.
Okay.
My phone is connected. You should be able to see my face from my phone. Like.
Okay. Anyway,
Yes.
let me appreciate your report and your nice presentation. It's a very good presentation. I was in hair cutting shop, barber shop, so I was just listening your talk. So, and I'm very happy to see so many of our students in this. Just watching your nice presentation, I think they will have a very good flavor of how to make good presentation. And I see many of these audience are fourth year students in our university. So it's a really very nice initiative. So I am just, I can explain myself how happy I am to see all of your initiatives. So it's a very good thing. And also this work is basically material science and molecular dynamics. It's not my very good place. I basically work on heat transfer or something like this. But anyway, it's a very nice presentation, and I just last 1 hour, I just keep on listening. So thank you so much. And also the organizers behind it. And also for my students, what I am very keen to say. So be brave and be confident through this kind of listening or joining or having some presentation as an audience. So I will leave this webinar soon with the best wishes for all of you who have a definitely very good effort and very good job in branding our students, Department of Mechanical Engineering. So actually, I must appreciate many of our graduates now living abroad, doing their PhD, masters, or even in teaching over there, to have a very good connection with our students to nourish their academic career. So on behalf of Department of Mechanical Engineering and all faculties of our department, I again appreciate the organizer of the souvenir and also the group MMMRN, right?
Yes, sir.
Okay. So you all are really doing excellent. Okay.
Thank you very
much. You are not just showing you what you are doing over there, but at the same time, you are making our students very brave in academic adventure. It's a very big thing. And I hope the cooperation from our graduate students, our alumni students with our current students will be even better and more stronger in coming days. So all the best from your teacher or from your senior, whatever you say. And I wish all the best for all of you. Okay.
Thank you very much, sir. Thank you very much for your words.
Thank you.
Okay. So we, Abrar Fayad, you raise your hand, ask your question.
Assalamualaikum. First of all, Bhai, I'd like to thank you for your amazing presentation. It's really interesting to see experimental works being done. As a fresh, going to be graduate, like not yet graduated, I'd actually like to ask you for some advice on approaching professors regarding wanting to do experimental works while having a computational background. Computational simulation-based material background.
I see. আচ্ছা অ্যাকচুয়ালি এই কোয়েশ্চেন কিউএনএ সেশনটা মানে আই মিন আমরা বাংলাতে কথা বলতে পারি সো এটা একটা এই কোয়েশ্চেনটা আসলে পার্টিকুলার কোনো অ্যান্সার আছে বলে আমার মনে হয় না। এটা এক একটা প্রফেসরের জন্য জিনিসটা এক এক ভাবে অ্যাপ্লাই হয়। অনেকেই আমাকে জিজ্ঞেস করে আসলে একটা প্রফেসরকে কিভাবে অ্যাপ্লাই করবে, এটা বলাটা ডিফিকাল্ট বিকজ এটার কোনো জেনারিক ট্রেন্ড নেই। তোমার পার্টিকুলারলি প্রফেসরকে কনভিন্স করাটা এক একটা প্রফেসরের জন্য এক এক রকম। এখন এই প্রবলেমটা অনেকেই এখন ফেস করতেছে যে বাংলাদেশ থেকে কম্পিটিশনাল কাজ করে এক্সপেরিমেন্টাল কাজে ঢুকতে যেতে চাচ্ছে। বাট এটা কোনো প্রবলেম নাই বিকজ আন্ডারগ্রেডের রিসার্চটা বাইরের প্রফেসররা এতটা ইম্পর্টেন্ট মনে করে না। তুমি ধরো একটা পিএইচডি একটা এক্সপেরিমেন্টে করে এসে তারপরে পোস্টডক করতে যাচ্ছ থিওরিতে, তখন এই ফিল্ড সুইচিংটা অনেক ডিফিকাল্ট হয়ে যেতে পারে। বাট এই আন্ডার গ্রেড থেকে তুমি মাস্টার্স বা পিএইচডি করো, তখন ফিল্ড সুইচিং এত ডিফিকাল্ট না বা এত ক্রিটিক্যাল বলে আমার মনে হয় না ওখানকার প্রফেসররা মনে করে। তো অল ইউ হ্যাভ টু ডু জাস্ট ডিরেক্টলি অ্যাপ্রোচ। তোমার এখানে যেটা ইম্পর্টেন্ট, তোমার যদি কোনো পাবলিকেশন থেকে থাকে, এটা অনেক ইম্পর্টেন্ট, বিকজ ইট শোজ দ্যাট তুমি যেই ফিল্ডে হোক ইউ ক্যান ওয়ার্ক অ্যান্ড ইউ ক্যান প্রডিউস থিংস দ্যাট আর ইম্পর্টেন্ট। সো তোমার যদি পাবলিকেশন থেকে থাকে, জাস্ট ডিরেক্টলি অ্যাপ্রোচ। আমি এতদিন এক্সপেরিমেন্টাল কাজ করছি, সরি থিওরিটিক্যাল কাজ করছি, এবং এগুলা থেকে আমি পাবলিশ করতে পারছি, এন্ড আই স্ট্রংলি বিলিভ যে আমি এক্সপেরিমেন্টাল কাজও ভালো করতে পারবো, এন্ড আমি করতে চাই। দ্যাটস দ্য মোর ইম্পর্টেন্ট ফ্যাক্টর। প্লাস তোমার একাডেমিক আরো যে সমস্ত অ্যাচিভমেন্টস আছে সেগুলো আইদার ইন দ্য ফর্ম অফ সিভি অর ইন এনি আদার ফর্ম তুমি শেয়ার করবা। আই থিঙ্ক দ্যাট শুড বি ইনাফ, সিন্স জাস্ট আন্ডারগ্রেড থেকে তুমি গ্রাজুয়েশনে ঢুকতে যাচ্ছ, সরি গ্রাজুয়েট পোস্ট ডক, আই মিন পোস্ট গ্রাজুয়েশন ডিগ্রিতে ঢুকতে যাচ্ছ।
রাইট। বাকিদের লাইক প্রেজেন্টেশনের বাইরেও যদি কোনো কোশ্চেন থাকে, এর পিএইচডি এক্সপেরিয়েন্স অথবা কোনো অ্যাডভাইস নিতে যদি চাও, তোমরা কিন্তু কোশ্চেন করতে পারো।
শিওর শিওর।
আর তোমরা চ্যাটেও লিখে রাখতে পারো কোশ্চেন তোমাদের।
Also, I'd like to ask another question. Direct ink jet printing এর যে direct inkjet printing এর যে prospectusটা আছে, ওখানে হচ্ছে কার্বন ন্যানোফাইবার ইনকর্পোরেটেড করে পলিমার সিনথেসিসের উপর এখন ফিউচার প্রসপেক্টাসটা অনেক ভালো। এখন ভাইয়ার কাজে হচ্ছে ডিসক্রিট ব্রোকেন আপ ফাইবার বা টার্বুলেন্স গ্রাফিনের যে স্ট্রাকচার গুলো ছিল, ওখানে হচ্ছে আমরা যদি মানে পিওর গ্রাফিন বা হচ্ছে বা গ্রাফিন ন্যানো টিউবস যেগুলো হচ্ছে ভাইয়ারদের মানে প্রজেক্ট থেকে এসেছিল, ন্যানো টিউবস যেগুলো এসেছিল, ওগুলো যদি আমরা ইনকর্পোরেট করি পলিমারের সাথে, দেন রেজাল্ট গুলো কি আরো বেটার আসার চান্স আছে বা ওরকম কিছু অ্যাকচুয়ালি জানতে চাচ্ছিলাম। বেসিক্যালি আপনাদের কাজের ফিউচার প্রসপেক্টাসটা।
আচ্ছা, অনেকগুলা কোয়েশ্চেন তুমি করছো, এগুলো অ্যান্সার একটা একটা করে দিই। ফার্স্ট অফ অল, ম্যাটেরিয়াল চেঞ্জ করলে প্রপার্টি চেঞ্জ হইতেই পারে, হওয়াটা স্বাভাবিক। সো কি হবে এটা আমি এখন না টেস্ট করে বলতে পারছি না, যদিও আমরা রিসেন্টলি একটা পেপার করছি অন এই যে ডিরেক্টিং রাইটিং অফ ইপক্সি এন্ড কার্বন ন্যানোটিউব। তো গ্রাফিন আর কার্বন ন্যানোটিউব দুইটা ডিফারেন্ট জিনিস, সো ওইটা একটু মাথায়। সো ওই সিএনটি ইপক্সের মধ্যে দিয়ে আমরা ওইটাকে 3D প্রিন্ট করে ওইটার স্ট্রাকচার, প্রপার্টি, এগুলো ইনভেস্টিগেট করছি। সো হ্যাঁ, প্রপার্টি অবশ্যই ডিফারেন্ট হবে। নেক্সট থিং হচ্ছে কি জানা ছিল তোমার আর 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 কোশ্চেন?
আপনাদের কাজের ফিউচার প্রসপেক্টাস বা কমার্শিয়ালাইজেশন মানে ফ্যাক্টরটা যেটা ইনক্লুড হয় আর কি।
হ্যাঁ, সো এই কাজটা বেসিক্যালি ছিল আমাদের, ওই যে তোমাকে বললাম না, আমি প্রেজেন্টেশনের শুরু থেকে বলে এসেছি যে আমাদের এখানে পেট্রোলিয়াম ইন্ডাস্ট্রি গুলা এখন মানে ক্রেজি ভাবে চাচ্ছে যে আমরা মানে সায়েন্টিস্ট এন্ড রিসার্চাররা ইন অ্যাসফাল্টেনের কিছু ইউটিলাইজেশন খুঁজে বের করি। তো এগুলো আমাদের ইনিশিয়াল এই 2 ইয়ার্স এর কি বল অ্যাটেম্পট ছিল তাদেরকে দেখানোর যে অ্যাকচুয়ালি প্রসপেক্টস আছে। এন্ড একটা জিনিস, এখন এগুলো সবকিছু আছে ল্যাব স্কেলে আছে, তো এখান থেকে কমার্শিয়ালাইজেশন হয়তো এটা ইন্টারমিডিয়েট অনেক অপটিমাইজেশন করতে হয়, এন্ড ওই অপটিমাইজেশন করাতে আসলে প্রপার্টি আরো অনেক সিগনিফিকেন্টলি বেটার হয় বা ফাংশনাল রেসপন্স গুলো অনেক বেটার হয়। সো অবশ্যই যখন কমার্শিয়ালাইজ হবে তখন প্রপার্টি এখন আমি যেটা শো করছি তার থেকে বেটার হবে, এবং এটা কবে হবে এটা রাইট নাও আমার কাছে আইডিয়া নাই, বিকজ এটা ভেরি ইনিশিয়াল কি বলবো periods of valorization of asphaltene. এখানে আমরা জাস্ট দেখাচ্ছি কি কি করা পসিবল। এখান থেকে কমার্শিয়ালাইজেশনে যেতে এক একটা ম্যাটেরিয়ালের কেসে এক এক রকম। যেমন দেখো সিএনটি কার্বন ন্যানোটিউবের রিসার্চ শুরু হয়েছে তোমার 90s থেকে, কিন্তু এটা কিন্তু এখনো কমার্শিয়াল ফ্যাক্টর মানে কমার্শিয়াল রেজিমে যাইতে পারে নাই। গ্রাফিনও এখনো যাইতে পারে নাই, 2004-এ প্রথম আবিষ্কার হয়েছে, এখনো যাইতে পারে নাই, যাচ্ছে ধীরে ধীরে, বাট যেতে পারে না। ওয়ারাজ একটা ডিফারেন্ট টেকনোলজি কিন্তু খুব তাড়াতাড়ি চলে যেতে পারে। সো এখানে অনেক কিছু, অনেকগুলো ফ্যাক্টর আছে বিফোর ইট বিকামস কমার্শিয়ালাইজড।
থ্যাংক ইউ ভাইয়া।
আর ভাই আমার আরেকটা কোশ্চেন ছিল যে আমরা মানে দেখতেছি যে আপনাদের এখানে এক্সপেরিমেন্টাল ওয়ার্কের সাথে হচ্ছে এমডি সিমুলেশন করা হয়েছে, একটা গ্রুপ করছে, তারপরে হচ্ছে কমসোলে এফইএম করছে। তো মানে একটা বিশাল কোলাবোরেশন মনে হলো। এন্ড এটা এই কোঅর্ডিনেশনটা, বাট এটার এক্সপেরিয়েন্সটা কি রকম? লাইক আপনারা বিভিন্ন ইউনিভার্সিটির সাথে কাজ করতেছেন একসাথে, এটার এক্সপেরিয়েন্সটা যদি শেয়ার করতেন। এটা কি ডিফিকাল্ট ছিল খুব, নাকি খুবই মানে দ্যাটস দ্য ওয়ে, ইজিয়ার ওয়ে?
ওয়েল, আচ্ছা জিনিসটাকে এইভাবে বলি, যে ভলিউম অফ কাজ দেখলে এটা 2 বছরে উইদাউট কোলাবোরেশন কখনোই পসিবল ছিল না। একদম স্ট্রেট ফরওয়ার্ড কথা, কখনোই পসিবল না। বাট অবশ্যই প্রবলেম আছে, প্রবলেমস আছে। যেমন হচ্ছে তুমি অনেক কাজ, তুমি ধরো আমার জন্য আমি নিজে একটা কাজ যত সফিস্টিকেটেড ওয়েতে করতে চেষ্টা করবো, ধরো একটা এক্সপেরিমেন্ট আমি 10 বার করবো, দেন আমি যেই ট্রেন্ড পাবো সেটার উপরে রিপোর্ট করব। আমি একটা আমার কোলাবোরেটরকে সেটা বলতে পারবো না যে আপনি 10 বার টেস্টটা করে দেন আমাকে, তাই না? এন্ড সে কোলাবোরেটরও চাইবে যে ওকে এটা তো আমার কোলাবোরেশন, আমি এই পেপারে লিড না, হ্যাঁ, আমি জাস্ট যত কুইকলি, অবশ্যই রাইট ওয়েতে, যত কুইকলি করা পসিবল আমি করে দিয়ে দিই। এটা ইনফ্যাক্ট আমরাও যখন কোলাবোরেট করি আমাদেরও থটটা ওইভাবেই থাকে, যে কারণ আমার তো মেইন কাজ আমার নিজের প্রজেক্ট, এবং যেখান থেকে ফান্ডিং আসতেছে, যেখানে যেইটার ব্যাপারে আমি লায়াবল। সো এরকম কিছু ঝামেলা আছে, এবং অনেক সময় কোলাবোরেটররা লেট করে, কেউ কেউ কোনো কোলাবোরেটর অনেক ফাস্ট থাকে, তাড়াতাড়ি করে দেয়, আবার কেউ অনেক লেট থাকে। সো ইটস এ ভেরি ডাইভার্স এক্সপেরিয়েন্স আমি বলবো, এক একটা খুবই খুবই ডিফারেন্ট।
আচ্ছা, আর আর কি কারো কোনো
একটা জিনিস হচ্ছে কোলাবোরেশন ছাড়া আসলে এত এত বড় কাজ করা,
হ্যাঁ ডেফিনেটলি দেখি বোঝা যাচ্ছে মানে প্রচুর কাজ এখানে।
কারণ আমি কিন্তু খুবই সারফেস দিয়ে কথা বলে গেছি, এই প্রতিটা যদি আমি ডিপে যাই এটা 5 ঘন্টা লাগবে আমার সব শেষ করতে।
জি ভাই। তো আর কি কারো কোনো কোয়েশ্চেন আছে? তোমরা ফ্রিলি কোয়েশ্চেন করতে পারো। আর আমাদের এই ওয়েবিনারের রেকর্ডিংটা আমরা আপলোড করে দেবো আমাদের ইউটিউবে, তো তোমাদেরকে দিয়ে দেওয়া হবে। সো ওটা নিয়ে ব্যাপার কিছু নেই, যারা মিস করছো বা নেটওয়ার্কের কারণে যাদের প্রবলেম হয়েছে they will get the feedback. So
এন্ড তো আমি এই যে চ্যাটে আমার মেইল আইডিটা লিখে দিচ্ছি, কারো যদি কোনো কোয়েশ্চেন থাকে আমাকে এখানে ডিরেক্ট করতে পারো, আমি অ্যান্সার দেবো। যে কোনো টাইপের কোয়েশ্চেন, টেকনিক্যাল কোয়েশ্চেন হতে পারে, অথবা অ্যাপ্লিকেশন রিলেটেড জিনিসপত্র হতে পারে, রাইসের ব্যাপারে, আমাদের গ্রুপের ব্যাপারে, রাইসের অন্যান্য গ্রুপের ব্যাপারে, জর্জ ওয়াশিংটনের গ্রুপের ব্যাপারে, আমি I'll do my best to reply and help. And definitely আমি মানে অনেক থ্যাঙ্কফুল MMMRN, তোমাদের এক্সিলেন্ট ইনিশিয়েটিভ। আমি ফেসবুকে একটা পোস্ট দিছি, এটা অ্যাকচুয়ালি আমাদের আরো অনেক আগে থেকে করা উচিত। এবং তুমি দেখবা যে ইন্ডিয়াতে অ্যাকচুয়ালি এই টাইপ অফ অ্যাপ্রোচ গুলা, স্টেপ গুলা অনেক আগে থেকে নিয়ে ওরা অনেক দূরে আগায় গেছে। আমরা অনেক লেট, বাট এক্সিলেন্ট মানে অর্গানাইজেশন এবং স্টেপ। এবং তোমাদের এটা আরো কন্টিনিউ করা উচিত, যতটা সম্ভব এক্সপ্যান্ড করা উচিত। ম্যাটেরিয়ালস, মেকানিক্যাল, কেমিক্যাল, অনেক অনেক ডিসিপ্লিনস আছে যেগুলোকে একসাথে করে এটাকে বড় একটা কমিউনিটি করা পসিবল। আমি খুবই ইন্টারেস্টেড টু হেল্প ইন এনি ওয়ে। প্লিজ ফিল ফ্রি টু রিচ আউট, এন্ড খুবই থ্যাংক ইউ ফর লেটিং মি টক।
থ্যাংক ইউ ভাই, এত শর্ট নোটিস আপনি আমাদের এই টকটা দিলেন, মানে খুব কম সময়ের মধ্যে। থ্যাংক ইউ ভেরি মাচ। আপনি তো ভাই এখন দেশে আছেন, রাইট?
আমি দেশে আছি, হ্যাঁ। আমার এই যে আমি একটু গ্রামের বাড়িতে আছি, আমার ইন্টারনেটের অবস্থা এই জন্য খুব একটা ভালো না।
ভাই থ্যাংক ইউ ভেরি মাচ ভাই, আর বুয়েটে আসলে অবশ্যই দেখা করবেন।
হ্যাঁ, শিওর শিওর শিওর, থ্যাংক ইউ সো মাচ।
থ্যাংক ইউ ভেরি মাচ। আর যদি কারো কোনো কোশ্চেন থাকে তোমরা ভাইকে মেইল করতে পারো অথবা আমাদের থ্রুতে জানাতে পারো। সো থ্যাংক ইউ ভেরি মাচ সবাইকে অ্যাটেন্ড করার জন্য। থ্যাংক ইউ ভেরি মাচ সাদি ভাই।
Sure. Thank you. Bye bye.